1,000 miles on a single charge and a full recharge in just 4 minutes. That is the claim. And if it is real, it changes everything about electric vehicles. No more range anxiety. No more long charging stops. No more planning your trip around charging stations. Just drive like a gasoline car, refuel in minutes. Go. Again, but here is the critical question. Is this a genuine battery breakthrough? Or just another headline designed to grab attention? Because we have seen big claims before: revolutionary chemistry, game-changing solid-state design, lab-tested ultra-fast charging, and then silence. No mass production, no real-world deployment, no vehicles on the road. In this video, we are going to break down what this 1,000-mile claim actually means, what battery chemistry might enable it, whether 4-minute charging is physically realistic, and what it would take to scale this technology globally. Before we go deeper, if you want realistic EV battery analysis that separates engineering reality from marketing hype, subscribe to the channel and turn on notifications. We break down the physics, not just the promises. Now let us start with the most important question. What kind of battery could even make this possible? What kind of battery makes 1,000 miles possible? A 1,000-mile electric vehicle range is not just a small improvement. It is a radical leap. Most long-range EVs today offer between 300 and 400 miles per charge. So to reach 1,000 miles, something fundamental must change. Not just software, not just efficiency, battery, chemistry itself. There are 3 realistic candidates being discussed in the industry. 1. Solid-state batteries. Solid-state batteries replace the liquid electrolyte with a solid material. Why does that matter? Because solid electrolytes can allow higher energy density. Improve thermal stability. Lower fire risk. Potentially faster charging. In theory, solid-state batteries could double the energy density of traditional lithium-ion cells. That means more range without increasing battery size dramatically. However, here is the challenge. Manufacturing solid-state batteries at scale remains extremely difficult. Many companies have demonstrated lab results. Very few have demonstrated mass production readiness. So if this 1,000-mile claim relies on solid-state technology, the question becomes, is it laboratory data or factory-ready data? 2. Silicon-dominant anodes. Traditional lithium-ion batteries use graphite anodes, but silicon can store far more lithium ions. Up to 10 times more in theory. By increasing silicon content in the anode, energy density increases significantly. This approach is more realistic for near-term scaling. Several companies are already integrating partial silicon anodes into commercial batteries. However, silicon expands during charging. That expansion causes stress and degradation. So engineering stable silicon-dominant batteries requires advanced material design. If solved, this could enable higher range without fully switching to solid-state chemistry. 3. Lithium-metal or hybrid chemistries. Some next-generation designs use lithium-metal anodes. These promise extremely high energy density. But again, stability and cycle life remain major obstacles. High energy density means nothing if the battery degrades quickly, and 4-minute charging adds even more stress to cell chemistry. Now let us connect this to real-world range. To achieve 1,000 miles, you need either extremely high energy density. Or an extremely large battery pack. An extremely large battery pack increases weight. More weight reduces efficiency. So the real breakthrough must involve improved energy density, not just size. Tesla and other major EV manufacturers continuously refine battery architecture, but even Tesla's latest designs do not yet approach 1,000 miles in production vehicles. That means this claim likely depends on next-generation chemistry, not incremental improvement. Now here is the critical point. Range is only half of the headline. The 4-minute charging claim may be even more difficult because ultra-fast charging creates enormous heat and stress inside battery cells, and physics does not bend easily. So next, we need to analyze the charging side of this equation, because if the chemistry cannot handle extreme current safely, the range number becomes irrelevant. Can you really charge 1,000 miles in 4 minutes? Now we move to the boldest part of the claim, 4-minute charging, not 30 minutes, not 15. Minutes. 4 minutes. Let us break this down using simple physics. If a vehicle has 1,000 miles of range, it likely needs a battery pack between 150 and 200 kilowatt hours, depending on efficiency. Now imagine charging a 200 kilowatt hour battery in 4 minutes. 4 minutes is 1/15 of an hour. So to fully charge that battery in 4 minutes, you would need approximately 3,000 kilowatts of charging power. That is 3 megawatts, for comparison. Today's most advanced fast chargers typically operate between 250 and 350 kilowatts. Even the highest commercial heavy-duty truck chargers are just crossing the 1 megawatt level. So 3 megawatts is not a small jump. It is a massive leap. Now let us think about what that means. First, heat. Charging at extreme power generates enormous heat inside battery cells. Without advanced thermal management, cells degrade rapidly. Second, infrastructure. Delivering 3 megawatts to a single vehicle requires industrial-grade transformers, grid upgrades, liquid-cooled cables, massive current handling systems. This is not something you plug into at a typical roadside station. This is closer to heavy industrial power delivery. Third, battery chemistry stress. Fast charging causes lithium plating in traditional lithium-ion batteries that reduces lifespan and increases safety risk. So for 4-minute charging to be realistic, the battery must handle ultra-high current, dissipate heat efficiently. Avoid long-term degradation, maintain cycle stability that requires not just better chemistry. It requires revolutionary engineering. Tesla and other EV manufacturers continuously improve charging speed. But even Tesla's most advanced systems today do not approach 4-minute full charging, and that is with years of refinement. Now here is an important clarification. The headline may refer to partial charging, for example, charging from 10% to 80% in 4 minutes under ideal conditions, or achieving a short-range boost extremely quickly. Those are different claims than full 1,000-mile charging in 4 minutes. Marketing language often simplifies technical nuance. So the real question becomes, is this claim based on laboratory testing under controlled conditions? Or is it scalable, real-world, infrastructure-ready technology? Because even if the battery can technically accept 3 megawatts in a lab, deploying that across thousands of public stations is another challenge entirely. And that leads us to the next critical issue. Even if the battery works, can it survive thousands of charge cycles? Because range and charging speed mean nothing if the battery fails after 2 years. If you appreciate clear physics breakdowns instead of exaggerated headlines, subscribe to the channel and turn on notifications. We analyze the engineering behind the claims. Fast charging versus long life, can both exist? Now we reach the part that determines whether this is a revolution or a short-lived experiment. Battery lifespan, because ultra-fast charging sounds exciting, but physics demands a trade-off. When you charge a battery extremely fast, 3 major stress factors occur. 1. Lithium plating in traditional lithium-ion batteries. Fast charging can cause lithium ions to deposit unevenly on the anode surface. This process is called lithium plating. Lithium plating reduces battery capacity, charging efficiency, long-term cycle life. In extreme cases, it increases safety risks. So for 4-minute charging to work safely, the battery chemistry must prevent lithium plating entirely. That is a serious materials science challenge. 2. Heat generation. High current equals high heat. Heat accelerates chemical degradation inside cells. Even with advanced liquid cooling systems, extreme charging rates create thermal stress. If temperatures spike repeatedly, battery health drops quickly. Tesla has spent years refining thermal management in its battery packs. Even so, Tesla's fastest charging is carefully controlled. To balance speed and longevity, 4-minute charging would require next-level cooling architecture, possibly direct cell cooling channels. Phase change materials, or entirely new pack-level design. 3. Cycle life versus performance. A real-world electric Vehicle battery needs to survive at least 1,500 to 2,000 full charge cycles. For a 1,000-mile battery, that could represent 1 to 2 million miles of driving. But if extreme charging reduces cycle life to 500 cycles, the economics collapse, replacing a massive high-energy battery pack would be extremely expensive. So the real breakthrough would not just be range and speed. It would be maintaining longevity under extreme stress, and that is rare. Now, here is an important reality check. Many battery companies demonstrate ultra-fast charging in laboratory settings, but lab cells are small scaling. That performance to automotive-sized packs introduces mechanical stress, thermal gradients, manufacturing inconsistencies, real-world temperature, variation. It is much harder than it sounds. Now ask yourself this: if this battery truly supports 1,000 miles of range, 4-minute charging, and long-term durability, then it is not just a product innovation. It is an industry reset, because such a battery would remove two major objections to electric vehicles: range anxiety, charging time inconvenience. But extraordinary claims require extraordinary evidence, which brings us to the next critical question. Even if the battery works technically, can it be mass-produced affordably? Because a laboratory breakthrough does not automatically become a global product. A breakthrough in the lab or on the factory floor. Now we reach the most important question of all. Even if this battery truly delivers 1,000 miles of range, 4-minute charging, long lifespan, can it actually be manufactured at scale? Because innovation in a laboratory is impressive, but innovation in a factory changes the world. Let us examine the real-world challenges. 1. Manufacturing complexity. Next-generation chemistries like solid-state or lithium-metal require new production techniques. That means new coating processes, new cell stacking systems, new quality control methods, new supply chains. You cannot simply convert existing lithium-ion factories overnight. Building new production lines costs billions of dollars. Scaling advanced chemistry from prototype cells to millions of automotive packs takes years, and even small manufacturing defects become massive problems at scale. 2. Raw material constraints. High energy density batteries often rely on advanced materials. If the chemistry requires rare metals or specialized compounds, supply becomes a bottleneck. Mass adoption requires stable global sourcing, affordable extraction, scalable refinement processes. Tesla has spent years vertically integrating parts of its battery supply chain for this exact reason. Even with that effort, scaling next-generation chemistry remains complex. If this 1,000-mile battery depends on rare materials, affordability becomes questionable. 3. Cost per kilowatt-hour. Current EV battery packs cost roughly $100 to $150 per kilowatt-hour at scale. 200 kilowatt-hour pack at today's pricing would cost $20,000 to $30,000 just for the battery. If the new chemistry is more expensive per kilowatt-hour, vehicle pricing could increase dramatically. For this to become mainstream, the new battery must either reduce cost per kilowatt-hour or deliver extreme longevity that offsets higher upfront price. Otherwise, it becomes a premium niche product. 4. Charging infrastructure upgrade. Even if the battery can accept multi-megawatt charging, the world's grid must support it. Installing 3-megawatt chargers nationwide would require grid upgrades. High capacity transformers, cooling systems, massive capital investment. This is not a small transition. It is an infrastructure transformation. And infrastructure moves slowly. Now, here is the key insight. Breakthrough batteries do not disrupt the market immediately, they disrupt it gradually. First call on low-volume premium vehicles, then pilot production, then scaled manufacturing, then widespread adoption. So when you hear 1,000 miles and 4-minute charging, the real question is not whether it works. The real question is whether it works. 10 million times. And that leads us to the final verdict. Is this a real turning point for electric vehicles? Or another over-optimized headline built around lab conditions? 1,000 miles and 4 minutes. What is the truth? So after breaking down the chemistry, the physics, the heat management, the charging power requirements, the manufacturing challenges, what is the real answer? Is this the world's first true 1,000-mile, 4-minute EV battery? Here is the honest verdict. It could be a real laboratory breakthrough, but it is not yet a mass market. Revolution. Let us separate excitement from reality, technically speaking. A 1,000-mile range is possible with next-generation high-energy density chemistry, 4-minute. Charging is theoretically possible with multi-megawatt power delivery, but combining extreme energy density. Ultra-fast charging, long cycle life, affordable, mass production. Global infrastructure readiness all at once. That is extraordinarily difficult. Tesla and other leading manufacturers have spent years improving battery systems step by step. True industry transformation usually happens incrementally, not overnight. Now here is the important nuance breakthrough. Announcements often reflect peak laboratory performance under ideal conditions, controlled temperature, optimized charging curves, small prototype, cells. Real-world vehicles face weather variation, manufacturing variability, user behavior differences, infrastructure limits. That does not mean the breakthrough is fake. It means commercialization takes time. If this battery truly exists at scale, here's what would happen next. Pilot production in limited fleets. Premium vehicle integration, gradual infrastructure expansion. Then broader adoption. The real sign of legitimacy will not be headlines. It will be factory announcements, supply agreements, charging station deployments. And vehicles on public roads. Until that happens, cautious optimism is the smartest position. Now here is the bigger perspective. Even if this exact claim proves slightly exaggerated, the direction is clear. Battery technology is improving rapidly, charging speeds are increasing, energy density is climbing, and the gap between electric vehicles and gasoline vehicles continues to shrink. So the correct conclusion is not skepticism and not blind belief. It is measured analysis, because the future of electric mobility will be shaped by physics, engineering, and economics. Not marketing slogans. If you want realistic AV and Tesla analysis that explains the science behind the headlines, subscribe to the channel and turn on notifications. Comment below. Would a 1,000-mile, 4-minute charging EV convince you to switch permanently to electric? Or do you still have concerns? In the next video, we will break down how close Tesla and other manufacturers actually are to solid-state production vehicles. That timeline might surprise you. So stay tuned. Thank you for watching. Stay informed, stay analytical, and I will see you in the next one.